Okay, so we are on part 2 of lesson 2 of our International University of Management Quantitative Methods 1 workthrough. So in this lesson, or the second part of lesson 2, we're going to be looking at summarizing quantitative data. In the previous lesson, we looked at a bar chart and a pie chart, and we're going to be looking at a couple of different ones in this lesson. Okay, so quantitative data provides numeric value in a study. You can read through this in your own time. Not too much to see there. It's just definitions, so it'd be good to know them. What is important though is the difference between a discrete variable and a continuous variable. So for a discrete variable, we say that's a variable that can take on an exact and countable number of numerical values, right? So things you can count. So is a variable whose value is obtained by counting. That is a discrete variable. So for instance, the number of cars in the parking lot, you can count them. The number of students at IUM, you can count them. Number of schools in the city, all of these things are countable. Number of students present, number of red marbles in a jar, number of heads when flipping 3 coins, students' grade level. Now this is important, the grade level, right? So that is this is sort of an interesting one. Let's just make a star at this one. Okay, so we'll make a star at this one. So you can't count a grade level, but that's sort of something to take into account there. That's an interesting one. Maybe go see if you can do some research on your own and see why this would count as a discrete variable. Okay, and the answer lies in the word level here. Because if you just have student's grade, that would be continuous because you could have anything between 0 and 100. But because it's a level, it's something specific and exact. A continuous variable, on the other hand, those are variables that can take on all values on an interval. Right? So it doesn't have to be any specific values, any value. So that's something you measure instead of count. So it's variable whose value is obtained by measuring. There we go. The rainfall figures. So again, so for rainfall, we could say we've got 300 milliliters of rain or millimeters of rain, or we could have 300.0012589. So you see, it's not an exact thing. It can be anything in an interval. Right, so that's why it's continuous. The number of cars come to a fuel point in an hour's time. This is also one on the continuous side that we'll make a star with. And again, for this one, go do some research and see why this would be a continuous variable. Perhaps you could look for something to do with Poisson distribution. So search for a Poisson distribution and see why that would be considered continuous in this case. All the rest of the things are pretty straightforward. The height of students, again, you could be 170 centimeters, you could be 169.5, you could be 169.03283, etc. So there's an infinite number of values you can take, not just a finite exact few. Weight, same thing, it's also something you measure, like 100 kilograms, or 70.23 kilograms. You can have any value. The time it takes to get to school, time is also a thing you can measure, like number of seconds or number of hours, and distance, also another thing you can measure. So height, weight, time, distance, rainfall figures, all those things you can measure, and they don't have to be an exact value or don't have to be any of a set of specific values. They could be anything in between. So for any two values you get, like the time it takes to school. Let's say it takes you on average, what do we say? Let's say 30 minutes to get to school. And someone else takes 25 minutes. So we don't know how many different types, how many different values there are in between, because there's an infinite number. Because we could have 27 is in between. So then how many values are there between 25 and 27? Well, depending on what you think, we might think, well, only 26 is between them. But we could also have 26.3 or 25.987, right? So there's an infinite number of values between any two other numbers. And that's why it's continuous. Okay, so that's the basic idea of difference between discrete and continuous. Discrete, you can count it, and continuous variable, you can measure it. All right, so discrete or ungrouped frequency distributions. Let's have a look at what this says here. In this form of distribution, the frequency refers to discrete value. Here the data are presented in a way that exact measures of units are clearly indicated. Okay, there are definite differences between the variables, like if we measure for integers, like 1, 2, 3, so there's an exact definite difference. The difference would be 1 if we're looking at integers. You can have 1 car or 2 cars or 3 cars, you can't have 1.3 cars, right? That's the basic idea of what they say here. An example we can look at: in a survey of 40 families in a village, the number of children per family was recorded. So we see it's all whole numbers, right? You can't have half a child. You can have 1 child, 0 children, 3 children, 2 children, 5 children, 6 children, etc. So these are discrete because you can count the number of children a family has. Okay, they ask us to represent the data in the form of a discrete frequency distribution. And we'll get to that. We'll see some examples later on. But the basic idea would be, in this case we could do exactly the same as we did in lesson 1, right? We could say the class or the category would be, you could have start with 0. 0 children, 1 child, 2 children, 3, 4, 5, or 6. And then we could say how many families. So our frequency, how many families have each number of children. So how many families have 0 children? It's 1, 2, 3 families have 0 children. For 1 child, 1, 2, 3, 4, 5, 6, 7. 7 families have 1 child, etc. And then you just count them, the same as we did in lesson 1. Okay. Then continuous frequency distribution. So for continuous, we can't do this, right? We can't have number 0 then the number 1, because what about all the numbers in between? There's an infinite number in between. So for continuous, we have to make intervals. We have to give an interval. So we have to say between 0 and 1, and between 1 and 2, etc. So here we go into some of the ways in which we do that. So a frequency table partitions data into classes or intervals and shows how many data values are in each class. Okay, so just like here, how many data values are in each class. The classes are just now an interval instead of just a fixed point. Okay, so let's just go through some of the definitions here. The lower class limit, that's the lowest data value that can fit in a class. Okay, upper class, highest data value that can fit in a class. Good, now the class width is the largest value minus the smallest value divided by the desired number of classes. So this is how you calculate what the class width will be if we want to have uniform class widths. And most of the times it's nice to do that because it presents well, but the class width doesn't always have to be like this. But for now, because this is what's in the student manual, this is what we'll use, a uniform class width. So each class will have the same width, and this is how we calculate that. Again, don't worry if you don't understand everything right now. We'll get to examples where we're actually going to calculate this. For now, we're just reading through some of the definitions. Now in B, always increase the value computed to the next highest whole number. So if you get like 9.7 as one of your answers, then we're going to make it 10. So the class width will be 10 instead of 9.7. So we're going to use whole numbers for class widths. Okay, class frequency. So that's the number of tally marks corresponding to that class. So the frequency again will just be you count how many things fall into that category, and that'll be your class frequency. The midpoint, that's the center. So let's say we had a class that goes from 0 to 10. Right? So from 0 to 10. If that's our class, what is the midpoint of this class? Well, it's halfway between 0 and 10, so the midpoint would be 5. And let's just do another one. Let's say it's some funny value like between 21 and 28. So how will we find the midpoint here? Well, the easiest way to do that is you just add these two together and divide that answer by 2. So this will be 49 over 2, so that'll give us 24.5. That'll be the midpoint of this class, from 21 to 28. Class boundaries. Now, we've already looked at class limits, so let's see what's the difference between a class boundary and a class limit. So upper class boundary, so we add 0.5 to the upper class, and for the lower class boundary we subtract 0.5 from the lower class limit. You see boundaries are bigger or equal to class limits. Okay, so if we had a class that's from 0 to 10, let's actually write that out. So 0 to 10. Let's make it 1 to 10. So 1 to 10. So our lower class limit would be 1, and our upper class limit would be 10. But our lower class boundary would be, we subtract 0.5 from this, so it would be 0.5. And our upper class boundary would be 10.5. Right, so that's important to know the difference between those two. Relative frequency, we already saw relative frequency in lesson 1. If we had a total of, what is lesson 1? We had 50 students total taking part in the survey, and each of them were asked what's their favorite subject, and 9 of them said mathematics. Okay, so our frequency table would be, our frequency would have mathematics, we'd have economics, we'd have accounting, etc. And so this will be, so this is our class or our category, this is our frequency, and our frequency for math was 9 out of the 50. So what's our relative frequency? The relative frequency, that's just the frequency divided by the total. So 9 divided by 50 gives us 0.18. So that is relative frequency. Okay. Example. Environmental gasoline consumption. The following data represent highway fuel consumption in miles per gallon, or mpg, for a random sample of 55 models of passenger cars. Use 5 classes. Okay, questions. Find the class width. Okay, yeah, so this is something we can actually quickly do. Okay, so 55 models of passenger cars, and this is fuel consumption. So we want to use 5 classes. And let's see, how do we find the width of a class again? Well, class width here says we take the largest data value minus the smallest data value divided by the desired number of classes. So largest data value, let's see what's the largest one we can find here. So for the 52, so 52 is our largest value. Ooh, 52 minus, what's the smallest value that we can find? Well, there's a 13, 10. 10 seems like the smallest one. The largest minus smallest, and how many classes do we want? 5 classes. So our class width will be 52 minus 10, so that gives us 42 divided by 5, and that gives us 8 point something. So it doesn't even matter what the point something is. We are told, let's just grab a look here again. NB, always increase the value computed to the next highest whole number. So we got 8 point something, so the next highest whole number will be 9. So our class width will be 9. Alright, so find the class width, that's going to be 9. Now the second question, make a frequency table showing class limits, class boundaries, midpoints, frequency, and relative frequencies. Okay, I think let's do that. Okay, let me do this. I'm going to draw a bit of a table here, and yeah, let's draw some values in here. So this is going to be in the class. Then we're going to have, what else do we need? So you're going to have class limits. So let's say it's a lower limit, upper limit, the lower boundary, upper boundary, the midpoint, and then we'll have, yeah, let's do frequency and relative frequency. Okay, that should be all of it. And let's just give our name, so that'll be our title column. And yeah, then we'll have our different classes. We've got 5 classes. So the first class, second, third, fourth, and fifth. Alright. Okay, let's see what we can do here. So this is going to be our class or our interval. So you can write class or interval, doesn't matter what you write there. Then we're going to have, what do we say, a lower limit, upper limit, lower boundary, upper boundary, midpoint, Then we'll have our frequency and our, well, I'm writing all uglier, frequency and our relative frequency. Alright, let's start filling in the values. So our first class is going to be from, our smallest value is 10. So it's going to be from 10 to 19, right? So it's a 9 difference. Well, it's actually a class width going to be 10, right? Let's see if does that make sense. Is that 9 values? Well, our class width, that should be, because 19 minus 10 is 9. Let's just see if we're told anything about inclusiveness. Numbers, value marks. No, that's fine. That's fine. Okay, let's see if this works. So 10 to 19, and then 20 to 29. Yeah, that's not. So if we do this, we see we're going up by 10 each time. But I'm just going to finish this, and then we're going to have a look back at this data and see if there's a problem or not. So then the next will be 30 to 39, 40 to 49, and 50 to 59. Okay. So the thing here is there's only going to be one value this way, is at 52 in the final group here, because this is actually, if we look at 10 to 19, how many values is that actually? Well, that's going to be 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So that's actually going to be 10 values. So let's redo that, and let's do that to 18, and then 19 to, so plus 8, 27. So now we can see, now we're going up in 9s, and then 28 to 36, and then we go 37 to 45, 46 to 54. Okay. So that actually makes a little bit more sense. Now we can see it's a bit more of an even spread. So now the lower limit, we said that's the smallest value that actually fits, so that's going to be 10. The upper limit here is going to be 18. What about the lower boundary and the upper boundary? Well, we said it's like the limits, but a little bit wider. So from 10, we're going to subtract 0.5, so that's going to be 9.5. And to the upper limit, we're going to add 0.5, so that's going to be 18.5. 18.5. The midpoint, how do we find the midpoint? Well, we say 10 plus 18 divided by 2. So the lower limit plus upper limit divided by 2. So that gives us 28 over 2, and that gives us 14. So 14 is the midpoint there. The frequency, now we have to go count everything that's from 10 to 18. Okay, so anything between 10 and 18 inclusive. So that one, this one, those two, and that's it. So 1, 2, 3, 4, 5. So that's going to be our frequency. And our relative frequency, so we know there's a total of 55 models. So our relative frequency is our frequency divided by the total. So 5 divided by 55, whoops, I want to get my calculator out here. So 5 divided by 55, that gives us 0.09. So 0.09. Alright, let me just do one more of these. I'm not going to do all of them because that's going to take a little bit too long, but I think you get the idea. Let's just do a different color for another one. Let's do blue, and let's do this one here, 37 to 45. So the lower limit 37, upper limit 45. So that's just the values you see right there. Lower boundary, we subtract 0.5 from the lower one, and we add 0.5 to the upper one, 45.5. Then the midpoint, again, we're going to add these two together, 37 plus 45 divided by 2. So that gives us 70 plus 12 is 82 over 2, and that gives us 41 as a midpoint. And you can see from 37 you add 4 to get to 41, then you add another 4 to get to 45. So we can see it is in the middle. And that's just a nice easy way to calculate it. Frequency, let's go count. 37 to 45, all of those. So, where are they? 37, only one. Okay, I might have missed something, but I think it looks like there's only one value in there. So the frequency is 1. And to find the relative frequency, again we say it's the frequency divided by the total. Okay, so we're going to have the frequency divided by the total, 0.02 if we round it off. 0.02. Alright, so that is about it for this one. Like, go and complete the rest of this one on your own, and let me know if you get stuck, or if you use any other method or a different way to complete this, or if you have any other questions just relating to this. Okay, let's push through and finish lesson 2 in this video still. So types of class intervals, the exclusive method. So the exclusive method, when the class intervals are so fixed that the upper limit of one is the lower limit of the other one. Okay, so what they mean by exclusive is that this value on the right is excluded from the class. Right, so I'm just going to underline all of them. So what this means is you go from 0 to 5,000 but not including 5,000. So all the way up to 499.9999. As far as you can go. In this case it will just be 2.99 because we're working with cents and rupees. So that value will be included, but 5,000 will not be included here, be excluded, and hence the exclusive method. 5,000 will only be starting in there. So when you have an end point and a start point, the end point is excluded, the starting point is included. So often we also write it like this. We'll go from 0, and then we'll have 0 is included, the lower bound is included. Then we've got our rupees, and then 5,000. So you see the 5,000 does not have that little equal sign, it's not included, but the left one is included. And then the next one, we would have 5,000 inclusive rupees, and then 10,000 exclusive. Okay, so that's the reason why we call this the exclusive method. And that always happens when the upper bound of one class is the same as the lower bound of the next class. The inclusive method, so that's what we had over here. So everything 10 and 18 and everything in between was included. And that happened because there were no values between 18 and 19. So with discrete values we can do the inclusive method because there won't be any values between 18 and 19. Right? But with a continuous variable there could be an infinite number of things between 18 and 19. So we have to go all the way up to 19 and then start again at 19, and then we'd have to use the exclusive method. Okay, inclusive, like we see here, 5 to 9, 10 to 14. So you see there's a gap between them. And that's fine. That just means that it's not possible to have something between 9 and 10. So in this case, okay, they don't tell us what this is or what these numbers mean. And that's fine. Open-ended classes, that's just something like below 2,000. So it doesn't say where it starts. It just says it's anything below 2,000 is in that class, and anything above 8,000 is in this class. So it's just open-ended. There's no limit, upper limit here, no lower limit there. Okay, charts and graphs. Pie chart, we're not going to draw these ones again, just see what they say here. Okay, we already looked at a pie chart in lesson 1 and a bar graph. Histogram. So a histogram is like a bar graph, except there are no spaces between the bars. So if we look at lesson 1 again, and we'll see in lesson 1 we did a bar graph, and it was something like this. So here you have your category 1, different categories, and your different levels of bar graphs. Now if we were to draw a histogram, we'd have category 1, well, category 1's lower bound to category 1's upper bound, and that would be something like this. So that would be for the first one. Then we'd have category 2's lower bound to category 2's upper bound, but it would be linked to this one, right? So that's a histogram idea. They're all linked, there's no gaps in between, and you've got an interval as your name for this. That's an interval. So here we actually have discrete categories or variables, and for a histogram we've got intervals. Okay, so here they give us approximate class width, maximum minus minimum divided by desired number of classes, gives us 9.5, so we round up to 10, which means we have a class width of 10. Like we see, it looks like 9 because 61 minus 52 is 9, but we saw earlier that actually is 10 values that we're actually looking at. Okay, frequency, relative frequency, that's always just your frequency divided by the total. Histogram for tune-up parts. Okay, so here we see we've got an interval as our name here, intervals for each ones, and no gaps between the bars, so that's why it's a histogram. Alright, and over here this is just our frequency again. So draw a histogram of this, so we can see, so this will be our lower and upper bounds. So the lower bound, we're going to see for the boundaries, we subtract 0.5 and add 0.5. So 125 minus 0.5 is 124.5, and then, so it's actually, you just write the starting value of each one. So 124.5, and then the starting value of the next one, 134.5, 144.5, etc. And then you draw your histogram with your frequency over here. So in this case, we'll have this will be obviously 6, that value. This value here will be 9. This value here will be 15, as we can see. This one here, 5. And this last one here, 2. So this is just our frequency on the vertical axis. Now frequency polygon, so that's just a line graph, looks something like that, right? So it's just series of dots like this, and you just connect them with straight lines. Straight line, straight line, straight line, straight line. That makes a frequency polygon. Polygon just means many gons, so many lines or many dots. Okay, number of suites, frequency. And now the interesting thing here is, where does the dot go? Does it go in the 18 or the 22 or somewhere else? Let's see here. The frequency polygon is plotted at the midpoint of the classes, right? So we see between 18 and 22 we've got 20. That's the midpoint. How do we get the midpoint? Just to recap, we say 18 plus 22 and then divide that by 2. So this gives us 40 over 2, which is 20. So that's our midpoint of this class. So at the midpoint 20, we have a frequency of 6. So 20 and 6, we see there. Then we do the next one. So the next one will be 23 plus 27, that's 50, divided by 2 is 25. So we'll have a point 25 on the x-axis and 14 on the y-axis. So 25 and 14, that's our next point. And then we just connect that with a line. And we draw our next one, so we connect all of those just with lines, and that's a frequency polygon. Component bar chart. So component bar chart is just like a normal bar chart, except we can represent a few more things with it. So a normal bar chart would be something like this, right? Let's say this was boys and girls, and let's say this is I don't know, so whatever the frequency thing is that we're measuring. Okay, so boys could be that value and girls would be that value, whatever that is. But for a component chart, we could say, well, what are all the different things? Let's say this is actually the spending. There's spending. Okay, so we see boys spend this much, girls spend that much. But maybe we're interested in what do they spend it on. So maybe we've got components, we've got entertainment, we've got food, and we've got, what else will we say here? I'm not even sure. What else can we spend money on? On each other. Okay. So let's just color code them. So let's say entertainment is green, food is pink, and each other is orange. Okay, so we can split it up. We can see maybe boys spend very little on each other, and so that'll be that component, but they spend maybe a lot on food, and sum on entertainment. So that'll be the components. And for girls, we can do the same thing. How much do they spend on each other? Let's say that much. And then on food, let's say they spend about that much, and on entertainment, that much. So this will be a component bar chart. So each bar has different components. So you can compare that as well as the total. You can compare the individual components. That's a component bar chart. So in this case, the components will be the years, the different years. So we'll have, let's see, there's a thing at the bottom. So for each year, will not be the components in this case. We could set it up like that, but it actually makes more sense to set it up like each category is a year. And then the components are these are the components, right? Property, plant, machinery, so number of dollars. So in 27, we can say 59,000 was spent on, what is this one here? Ooh, I'm not even sure, that property. Then 176,000 was spent on plant and machinery, or as cash, etc. You can see this, right? These are the components in each year. So you can see there's a general trend going upwards, and then you can see some of the things are maybe getting smaller or bigger. This one is staying really constant, starting to grow over here. This one also grows a little bit, but as you can see, there's a decline in that part, even though there's an increase in total. A big increase there, decline here, decline here, decline here. So only that one was increasing in this year. So it's useful to have a component bar chart for some cases. Okay, and then stem and leaf, and I think that's the last thing. Okay, I know this is quite a long lesson and we didn't even do much, but at least we just saw how the different representations of data work. So stem and leaf, if you get given all your data, then you can make a stem and leaf plot. So this represents your tens and this represents your units. So in this case, some of the values would have been, let's say 52, 57, 62, 62, 62, 62, 65, 66, etc. So if we were going to go draw this in a stem and leaf, we'll go, okay, there are the tens, we've got 5 here, then we've got a 52, we've got a 57. So that's how we get that part. Then for the sixes, we've got a 62, then another 62, another 62, another 62, then a 65, then a 66. So that's how you draw your stem and leaf. So just quickly, let's maybe do one more. Just pick a couple of random values. Let's say 13, 14, 21, 27, 28, 33, 35, and then 40, 41, 41, 43, 47. And maybe let's just do a 58. Okay, stem and leaf. So we've got a 1. And then which ones do we have with 1? We've got a 13 and we've got a 14. Then next we've got a 2 for 20s. And then we've got a 21, a 27 and a 28. And then for the 30s, we've got a 33 and a 35. So 33 and 35. For the 40s, we've got a 40, 41, oops, the 41, another 41, 43 and a 47. And then for 50s, we've got a 58. So this is your stem and leaf diagram for this data right here. Okay, so again, a long video and we still haven't gotten to the nice things yet, but it's important to be able to know what they mean when they ask you some of these basic questions. Very important in this lesson, the difference between continuous and discrete data. Right, so again, just discrete data is something you can count, or a continuous variable, that's something you measure, but you cannot necessarily count. Alright, and then next time we'll look at lesson 3. Now we're getting to actually some nicer calculations in lesson 3. So I'll see you again shortly for that.